Okay, so we started the recording a little late. We already had this question over here. Evaluate whether each statement is correct or incorrect. Okay, here's the next one. The sublimation of dry ice, which is the same as solid carbon dioxide, involves an increase in entropy. Is that a correct statement or is it incorrect? What do you guys think? There's somebody typing out there. What do you guys think? First of all, what is sublimation? Do you remember? Nobody? Anybody? What is sublimation? It's when you convert solid into gas, right? Solid to gas. So therefore, it's correct, right? We said that pretty much any conversion of any physical state into gas is going to proceed with a huge increase in entropy. Cool? Questions? No? We're good? Okay, next one. Sorry, I have a screen over here and a screen over here. A 1 mole sample of SO2 gas would have greater entropy than a 1 mole sample of SO3 gas. Is that correct or incorrect? What do you guys think? Tell me. Give me a thought. What do you think? These are both gases, so physical state is not an issue here. Same amount of particles, 1 mole each. So that's not an issue. So what would be the issue here? Any thoughts? No? So we're going to say that this is incorrect. Why is it incorrect? What is the factor that's at play here between these two species here? Let's see, I got chat here. All right, so yeah, it's the same, but it's not because they have the same entropy. They do have different entropies. See if we remember why. So here, molecular size is the issue. Sulfur trioxide is a bigger molecule. So more possible, let's say, distributions, or we call them states, right? So more possible distributions of the electron clouds. Okay, don't forget that there's several things that we deal with here. I hope my audio is not fading out. Remember, you have physical state affects entropy. Temperature affects entropy. Size or complexity of the molecules affects entropy. All right, don't forget there's all these different things that you want to be aware of. All right, let's go to the next one here. Here's a few more. Here's another statement. Dissolving KCl in water would have a negative entropy change. Let's see, what's our thought here? Dixie, the first one, yes, the first one was incorrect. We said that it was incorrect because spontaneity is not the same as instantaneous. So Having a negative delta G means it's spontaneous. Doesn't mean we're going to be able to observe it necessarily. Okay? Cool. All right, so dissolving KCl in water would have a negative entropy change. What do you think of that one? What happens when you dissolve an ionic compound in water? What does it do? We just studied this for a whole unit. Solubility. What does it do? Any thoughts? No? So, dissolving, well, let's say this is incorrect, right? We said that dissolving creates more states. Sometimes we call them distribution. So now you have from a crystal structure that is very ordered, very well organized, to essentially ions, kind of like floating around in the solvent. So you have an increase of entropy. All right, let's take the next one. We did a similar one to this one last time. So here's a reaction. Notice that it all happens in the gas state. So we have CH3OH decomposing to CO and hydrogen. And it says here that reaction will be expected to have an increase in entropy. What do you think is the driving force here? First of all, is it correct or incorrect? What do you think? You guys are so quiet.
Correct, due to number of moles.
Number of moles of gas, specifically. Okay, don't forget that. The number of moles per se is not an indicator, but the number of moles of gas. So we could say that this is, oops, got the color here. This is going to be correct because there's an increase in the number of moles of gas. Very good. Okay, don't forget, it's a very quick look at the reaction, and if there is an increase in the numbers of moles of gases, the delta S is going to be positive. If there's a decrease, delta S is going to be negative. If it's the same number of moles on both reactants and products, you can't predict. But whatever the case, whether it's positive or negative, it's very likely going to be a very small number. All right? Okay, let's take the last one here.
Can you repeat that again? You said that it is something about S. Sorry, I was writing.
You take a quick look at a chemical equation. An increase in the number of moles of gas indicates an increase in entropy, a positive delta S. A decrease in the number of moles of gas indicates a decrease in entropy, so a negative delta S. And if the number of gas moles is the same, you cannot predict what the change is going to be, but whatever it is, whether negative or positive, it is going to be a small change. All right, got that?
Got it, thank you.
Okay, no problem. So last one, a reaction with a positive delta S will be spontaneous. Is that correct or incorrect? Letting me do all the work here.
True. Oh, never mind. Sorry.
Why is that incorrect? I mean, it could be, but having a positive delta S, does that automatically mean that it's spontaneous?
No.
No, right?
Because it's
Remember,
dependent on delta H as well,
very
whether
good.
delta
Okay,
H
so
is
two
endothermic or
reasons for
exothermic.
it. Yeah, two reasons for it. One, it also depends on enthalpy change, right? The heat of the reaction. The second reason is that the second law says that it's about the change of entropy for the universe. In other words, a system may have an increase in entropy, but if the surroundings do not have an accompanying favorable change, the overall entropy of the universe would not be increasing, and therefore the process would not be spontaneous. And again, remember, when we talk about reactions, we mean in the direction that is written. It's very important. In other words, if it's a reversible reaction, we write it the other way, that process will be spontaneous. So in other words, yes, a reaction with the positive delta S could be spontaneous, but it doesn't automatically default to being spontaneous because that's not what the second law of thermodynamics tells us. All right, cool. So these are things that I want you guys to be always thinking about. I think those of you who've been with me for a while know that uh, I look at this as a chemistry, not a math class. And although you have to solve a lot of quantitative problems, I really want to make sure that you're not kind of just basically plugging numbers into equations, solving them, and voila, here's a number, without really thinking behind uh, into the concepts that are driving these types of things. All right. So with that in mind, let's do this little review here. I think we talked about this last time. I just wanted to see. Let's go ahead and fill up this table. So that over there on the top is what I call the equation, right? That's the equation that essentially encompasses all of that the second law of thermodynamics teaches us. And it relates the four major categories, the free energy, the heat of reaction or enthalpy change, the entropy change, and the temperature, which is very important as we saw. The temperature might determine whether a process is spontaneous or not because it helps us connect the entropy of the system with the entropy of the surroundings. So what we've drawn here is we have four scenarios. We've done it for, okay, what if delta H is negative or positive? And then what if delta S is negative or positive? And then we are looking at it at low and high temperature. Okay, so let's go ahead and get started. You tell me. Let's start with the first row here. We have a negative delta H and a positive delta S. Remember, the goal is that the values of delta H, delta S, and T need to all add up in that equation to a negative delta G. So if delta H is negative and delta S is positive, what's going to happen here to the equation? When do we get a negative delta G? Think about it quick. Shouldn't take very long. Always, right? Mathematically. If delta S is positive, right? That number up there, delta S is positive. This number here is always going to be subtracted, so it's going to be negative. Delta H is negative, so that means that the process is always going to give me a negative delta G. Got it? Okay, let's take the next one. It's a little tricky now. Now we have a positive delta H and a negative delta S.
It is
Remember,
never spontaneous, but the reverse is.
very good. In other words, the process as written can never give me a negative delta G because delta H is always positive, and then the minus T delta S essentially ends up adding something else. So basically, you're going to be non-spontaneous under all conditions. Very good. All right, next one. What if they are both negative? So remember, a negative delta H typically is favorable. So an exothermic process, as we explained, means the energy drops, which typically indicates a decrease in energy relates with an increase in stability, right? You're going from a higher energy to a lower energy state, which is more stable. But then you have a negative entropy change here. In other words, the entropy is going to kind of like corrode that negative delta H. When you subtract this, right, it's going to be minus a negative, so it's going to be plus, which means it's going to make the equation less negative. So what do I need to do if the temperature is low? What's going to happen? Is that T delta S factor going to have a big impact?
Yeah, because it's only spontaneous at below critical temperature. So if you have a lower temperature, it should be spontaneous. And if you have a higher temperature, then it's non-spontaneous.
Very good. In other words, if T is a low value, that means that that T delta S factor is going to be small. So it's not going to affect the contribution of the negative delta H. So at low temperature, it's going to be spontaneous. But if you increase the temperature past a certain threshold, now that T delta S factor becomes very significant, and it might flip the value into the positive realm. So we would expect that at a high temperature is non-spontaneous. And again, in this table, low and high temperature are relative, right? You have learned, and we'll do a little practice where you calculate, well, what is the actual temperature at which it flips. Okay, the last, yes, question?
Hey, Professor, I have a question. So regarding the non-spontaneous, is that the same as when delta G is equal to 0?
Well, what does delta G equals 0 represent?
Equilibrium.
Equilibrium, right? So,
So that's non-spontaneous.
remember, we'll discuss it later in practice. Remember that delta G is specific to certain conditions. And so many times what we actually ask is, where is the system with respect to its equilibrium position? So is delta G positive? Is it negative? Now, which way is the system going to go? Is it going to go forward or in reverse until it reaches that equilibrium point, right?
Yeah,
So,
I guess I'm kind of asking this because of last night's quiz.
mhm.
I wasn't sure if you're trying to get it to be at equilibrium to determine that. So this is part B. If you're getting it to be at equilibrium to be non-spontaneous, or are you trying to look for when G is a positive number, meaning it's non-spontaneous?
Delta G equals 0 means that's the point at which this schematic changes from spontaneous to non-spontaneous.
Okay, great.
It's algebra. We're setting delta G to be 0 to see at what point does the temperature make the equation switch.
Okay,
Right?
perfect.
Okay,
Yeah,
so the last
yeah.
one here is
Thanks.
when both the delta H and the entropy are positive. Remember, a positive entropy change in the system is favorable. Of course, remember that we had to consider, well, what about the surroundings? A positive delta H obviously is not favorable because it means I'm increasing energy. That means I'm going from a less to a, I'm sorry, from a more stable to a less stable state. So in this case, again, mathematically, delta H is positive. So that means that I need to see what contribution does that T delta S factor need to make. So if that temperature is low, the T delta S is going to have what? A high or a low impact? This is just math here. There's no underlying physical reason, just math. If delta H is positive and I want the equation to be negative. What happens if the T delta S factor is very small? You get very little impact, right? So therefore, at a low temperature, it's non-spontaneous because the T delta S is not sufficient to turn that positive delta H into a negative value. Now, what if the temperature is high enough so that the T delta S now becomes a significant contributor?
It would be spontaneous.
So it'd be spontaneous at a higher temperature, right? So this is the typical situation with some processes that we study where they don't occur at low temperature, but they are good at higher temperature. Okay, cool. Okay, let's see what the next one is here. Oh, for this one I have a kind of like an example of the application of what we just talked about. So again, we're going to use our equation here. And this is a reaction that happens during the extraction of copper from some of its ores. Unfortunately, in our Chem 1B class here at Long Beach City College, we don't get a chance to look at these processes of how do we extract metals from the ores that we mine. So most metals exist in nature in the oxidized form, like copper ions, for example, iron ions, all of them. There's no iron or copper out there on the earth, right? It's all oxidized. So essentially, we had to reduce them to bring them into the metallic state. And this is one of the reactions here. You've basically converted the ores into a copper 1 oxide. And then what you do is you treat them with carbon graphite, which actually it's a mixture called Coke. No, it's not the drinking one or the other one, I'm talking about. So this is the way it works, and this is how you obtain copper, and then you have carbon monoxide being generated, which is actually reused to continue some of the process of reduction. Okay, so it says here delta H is 58.1 kilojoules, and delta S is 165 joules per Kelvin at 25 degrees. Is the reaction spontaneous at 25 degrees? Is the reaction spontaneous? And if not, at what temperature will it become spontaneous? Okay, I'm going to do this. I'm going to copy this into a different place. Let's see if I can get this thing to work. I kind of lost my. Every time that I do this, I lose my cursor. Oh, there it is. All right, so I am going to change this. I copy it over to a different thing here if I can find it. There we go. Okay, what happened here? Okay, I got it here. So let me see if I can simply copy it here. No, it won't. Oh, there it is. Okay. All right. So I have here the extraction of copper. So here's the question again. So how do you answer this kind of question? First of all, is the reaction spontaneous at 25 degrees Celsius? They give you delta H, they give you delta S. What do you need to do?
Um, it's not spontaneous because after using the equation, the Gibbs equation, you would get a positive number, which would be 8.93.
Okay, let's try that out. Let me see if I can get this thing to work. Okay, so basically what we're going to do is we're going to calculate this. We're going to say delta G equals delta H minus T delta S. So that would be 58.1. Now be careful, this is kilojoules, right? And let me see if I can make a little room here. Slide this a little bit here. There we go. Let's go back here to our 10. And this would be then minus T, which is 25, but remember you have to convert that into Kelvin. So 25 plus 273. I'm going to cheat here and just put 273. And then the entropy is 165. But this is joules per Kelvin. So we had to convert that into, oops, sorry, kilojoules, right? Make this a little smaller. There you go. So we have to take kilojoules. So remember that it's 1 kilojoule is 1,000 joules. Okay. So I'm gonna let you guys do the math there. What did you get, AG?
8.93. Yeah, 8.93.
8.9 kilojoules. Right. What is this thing? 1 second. Something popped in my screen here. Sorry. Kilojoules for this reaction. So in other words, it's positive, which means that it is non-spontaneous. Very good. So that's the way you answer this kind of question. All right, you just plug the numbers they gave you in. The trickier version of this question is one where they give you, the delta H of formation, the standard entropy. So you have to calculate what is delta H, what is delta S, and then you have to calculate what is delta G. That's kind of like the one that we did on Tuesday. At what temperature would it become spontaneous? So this is where Aini, you were asking earlier on. So essentially, what we call the critical, or I call it the flip point, right? So basically, the flip happens whenever delta G becomes 0, correct? So at that point, that's when it switches, that's when it flips. Oops, sorry. So what we want to do is we want to see, okay, let's see, up a little bit here.
That's the T equals delta H over delta S, right?
So basically, right. So if 0 is the point when that happens, delta H minus T delta S, we want to solve for, okay, at what temperature does that change happen? So that temperature would be essentially, right, it's going to be minus delta H divided by minus delta S. Okay, so you can put the numbers in there. I'm sorry, I have a free version of this Miro board, and it keeps flashing all kinds of ads and stuff on it. So let's put in the numbers again. This is 58.1, but that was kilojoules. So we want to change this one over here, the 165. I'm going to divide by 1,000. This will be kilojoules, and this will be kilojoules per Kelvin. So the Kelvin are going to flip up. And let me have you guys do that math in there. What do you get?
352.12.
Okay, everybody else get that number? Yeah. So again, let's respect sig figs here. So let's say it's going to be So again, the idea here is, remember that we said a positive delta H with a positive delta S will be spontaneous at higher temperature. It was obviously that at 25 degrees Celsius, which is 298, it didn't work. So you have to bring the temperature up to about 352 Kelvin, which is essentially about 79 degrees Celsius. I mean, it's not super mega hot, which is very favorable for us. And again, like I said, we don't get to study this kind of stuff in class, but it's a very interesting process. How do you obtain metals that are so useful for making, I don't know, copper pipes and what have you, uh, from the earth, where the copper is present in the form of different minerals, different compounds where it's oxidized. So essentially, you had to do is heat it at a temperature higher than this, in the presence of this carbon mix that we call coke, and it goes through, and we obtain. I mean, this is just one reaction, and there's a few other processes that are involved, but this is one way of doing it. I just wanted to give you this as an example of how to do these kinds of questions. So again, remember that when given this kind of question, the goal is, let's find out what delta G is. Is it positive or is it negative? And then if it is positive, at what temperature would it be negative? Or sometimes it becomes obvious if you have a positive delta H and a negative delta S, you'll say, it's never going to be spontaneous at any temperature. So it's important that you remember that table that we built earlier on. All right? Cool. Any questions? All right, let's do another one here. Let's see if I can change this here. Oh my gosh. Totally lost my cursor again. Okay, let's see if I can do this. Sorry guys, I'm kind of lost here. There it is. Over here. Okay, here we go. Back here. All right. So that's what we had. And let's see what the next question was. Okay, this is another one of the equations that we use. This one is, we derive a relationship where we saw that for the standard enthalpy, for the standard free energy, which is the free energy under purely, we said, what happened is I lost my mouse here. It will not work. We said that for the standard free energy, which is the one that has that little superscript 0 there, we got delta G naught, we can find a correlation between it and the equilibrium constant. So here's another one of those chemical reactions that are useful in industry. Sulfuric acid is perhaps the chemical that is manufactured in the largest amount industrially in the United States, or it used to be. I don't know if it's still there, but it used to be. And this is one of the reactions that are used. This is the combination of sulfur dioxide with oxygen to produce sulfur trioxide. It's only a step in the process. Reaction has a delta G naught of minus 141.6 kilojoules at 25 degrees. So I want you to calculate what is the value of the equilibrium constant at 25 degrees Celsius. I'll give you a few moments. You just want to plug the number in. You have to convert T into Kelvin. And don't forget, what is the value of the R constant. Remember, we're going to use the thermodynamic value, right? Forget. Let's see. I'm having a really hard time with this because I lost my mouse is not working anymore. All right. In the meantime, I'm gonna do while you guys work on that. Come here and I'm gonna do some manipulations here. Sorry guys, I'm working something out here. Trying to see if I can. I'll tell you what I'm gonna do is I'm gonna go here, oh, there we go. Okay, let me. You guys got it? Okay, now I gotta find this control again. I am so sorry. My systems are all out of whack right now. There it is. Come on. Okay, let's bring it over here to this board. There we go. All right, so what did you guys get? We have delta G naught equals minus R T log of K. But remember, in this case, our unknown is actually K, not delta G naught. We already have delta G naught, so we have to solve for that, right? So again, we can go, log, oops, sorry. We can go log of K is delta G divided by minus RT, correct? They give us minus 141.6 kilojoules per mole. You gotta be careful with the units because when we divide by R, which is 8.314, and this value, of course, is a constant. You guys don't have to know this. It would be given to you in a quiz or exam, or you'd have to look it up. So this would be joules per moles per Kelvin. I don't know if you remember from your Chem 1A class, the typical value that we use, the 0.008206 liters per atmospheres per mole per Kelvin. Remember that the product liters atmosphere is a unit of work. It's a unit of energy. And 25 degrees, we know it's 298 Kelvin. So what has to happen here is we need to convert negative over here this into joules, so it'll cancel with the joules over here. Gotta be careful with those units. Right? That's joules, that's kilojoules. So let's convert that. We're gonna say that it's 1,000 joules per kilojoule. I'll make sure the units cancel out, correct? So let's make sure the units cancel out. Kilojoules with kilojoules, joules with joules, per moles with per moles, and Kelvin with Kelvin. That's very important because remember that the logarithm of a thing, shouldn't have any units. Okay. And I don't know what the next step is. Oops. So you're going to calculate that, and then you're going to find out what K is, correct? Oops, sorry. K is going to be, E to the minus, whatever that thing was. I'm sorry, not to the minus, to whatever that exponent was there. Again, I'm letting you guys do all the algebra here. What did you get for K here? Well, I think the number is supposed to come up. It's a huge number. It's going to be like 7 times 10 to the, I think, 24 or something like that. This number comes up here to about 50 something. Did you guys get that more or less? I'm trying to make this not a math class, so I'm not trying to teach you how to do things because, again, everybody has different calculators. I'm just trying to guide us into how to do these things. Are we all there? Cool? Okay. So what I'm going to do now is I'm going to ask the last question here, and we'll see if we can get this over with. Sorry that I've had so many technical difficulties. Now the problem that I have is that, see what, I'm going to stop the share and I'm going to go back, start it again. So I can't find the cursor here. Okay, so we're going to go back to our board here. There we go. So we already established what the K is, right? But we said that relationship is only valid when the system is at standard conditions. So the equilibrium constant correlates with the standard delta G. But most of the time, a system is not at equilibrium. And so we use this other expression, delta G equals delta G naught plus RT log of Q, where Q is the reaction quotient. It's the same formula they use for calculating the equilibrium constant, but the difference is that it is with the concentrations or pressures at whatever condition they tell you. You don't know if it's equilibrium or not. Okay, so here's the question. I have a container. I filled it with the three gases at different pressures, 25 degrees. And the question is, in which direction will the reaction proceed to establish equilibrium? And what is delta G for this system? So you're going to have to remember how to calculate that. So while you're doing that, so while you guys do that, I'm going to come over here and copy this over to our board. All right, so let's come here back to this board here. Again, if I'm able to find my cursor again. There we are. Bring us back here to the Miro board. Copy the question over here. Okay. So what do we need to do here? How do we find whether the system is going to move to the right or to the left at equilibrium? What do you compare with what? K versus what? Gaussian quotient, right? That's what we use to establish. If the system is at equilibrium, then the calculation will give us the same value as K. If it is not an equilibrium, the calculation of Q is going to give us a different number. So let's see what Q should be for this reaction here. Okay, you have, I'm missing the double arrows here. Sorry about that. Kind of disappeared on the conversion here, but you have the pressure of SO3, that's a product, squared, right, divided by the pressure of SO2 squared times the pressure of O2. You all remember that formula? I've always told you chemistry is always cumulative. We learned this back in unit 14 when we introduced equilibrium. So you have to remember how to do these things. Remember, it's the either the pressures or the concentrations of products over reactants. Each one of those elevated to an exponent that's equal to their coefficient on the balanced equation. Okay, so SO3 is 0.1. Hold on. Now I'm having a hard time making my cursor work. Now I'm having a hard time with my stylus work. So this one is 0.1 atmospheres. The SO2 we said is 0.500 atmospheres squared. And oxygen is 0.0100. Okay, so if you do that equation there, what do you get? This is just algebra here.
Four.
Very good. That's what I got. I also got 4. So how does 4 compare to the value we had obtained before for the for the equilibrium constant, which was 7 times 10 to the 24? Much, much less, right? Oops, sorry. Much, much less than the equilibrium constant. So if the reaction quotient is smaller than A, which way does the reaction have to go? Does it have to make more product, or does it have to go back and make more reactants? What do I need more of? Yeah, products, right? Remember, guys, these are things that you guys need to know. This is old stuff. I need more products. Remember, it's a ratio of products to reactants. If that ratio is too small, that means that I need to increase it. And the way I increase it is by making more products. So therefore, the reaction goes to the products. Okay? So again, I'm trying to get you guys your gears in place. We're almost out of time. So let's see if we can do the next one here. Oops, sorry. What am I doing here? I seem to be able to kind of grab this guy here, way down here, and then move the rest of the stuff up. Let's grab this guy. Oops. Can't seem to be able to grab just this guy here. Okay, so our next question is, what is delta G for this system? Well, we have the equation, right? We said that delta G equals standard delta G plus RT log of Q. So we already have these values, right? We have this guy is minus 141.6 kilojoules per mole. And we said Q equals 4. Remember that all of these expressions of equilibrium constants or reaction quotients, we don't go with units. Okay, so, and don't forget, R is, again, 8.314 joules mole Kelvin. So that means that we had to either convert that to kilojoules or convert the other one to joules. So you should be able to solve that, and you should get a result that delta G, sorry, gosh, I can't move this thing anymore. Okay, I'm trying as hard as I can. There we go. So delta G, I think once you do the math, should give you a value of about 1 minus 138 kilojoules per mole. As you can imagine, if Q has a value of 4, which is a relatively small number, that RT log of Q value is not going to be very significant, so it's not going to change delta G that much. So the process is still spontaneous, as we established. It's going to go towards the products to reestablish equilibrium. It's just going to require a little less energy than in the standard state. Oh gosh, my dog just went crazy here, and you're probably hearing her through the microphone. Sorry about that. Okay, so I apologize for the technical difficulties here. Like I said, I don't have very high quality equipment, but I will take this recording and post it later so you guys can follow it along. Let me see if there's any questions. Twice over here. Any other questions?